In this video, we're going to talk about global maxima and minima. We've already talked about local or relative extreme values, the maximum and minimums. Now we're going to talk about global. Some people use the term absolute instead of the term global. And so sometimes you'll see people say absolute max or absolute min. And sometimes I'll use that word as well. But absolute and global, similar definitions here. So it says these definitions follow very similarly to the definitions for your local max and minimum, but we are going to have global instead. So it says for any function f has a global minimum at p if f of p is less than or equal to all values of your function, right? So that means f of p is the smallest y value of all of your functional values for all x where your function is defined. And this little symbol here just means for all x. For your global maximum, it says f has a global maximum at p if f of p is greater than or equal to all your functional values for your function here. So I can say f of p is greater than or equal to f of x for all x. And so it's not just those x values that are the y values that are near it, it's for all of the y values in the whole data set. And so when we try to find out what our global max and minima are, or if we have any, we have to pay attention to whether we have endpoints where our function is defined. And so we can have either a closed interval, which is in this case here, or we can have an open interval, right? When we have a closed interval, that means that we have endpoints, right? And we include those endpoints. Our global max and mins are going to be coming from either a critical point, which is where your derivative equals zero or is undefined, or an endpoint of that closed interval, right? So for instance, when we have this closed interval here, we see that this point right here, this point right here, and this point right here, they're local maximum values because they're bigger than, they have y values that are larger than all of the y values that are near it, right? For this function here, right? However, since we have three of these and we have an endpoint, this one right here is also the global maximum because it is the largest y value, right? So the global maximum is the point with the largest y value. And you're always going to be guaranteed one when you have a continuous function defined on a closed interval, all right? You're always going to have a global maximum and you're always going to have a global minimum. If we look further at these 2 points here, these are critical points. And both of these will be local minimum values. And then the one that has the smallest y value or the lowest point is going to be your global minimum, right? That is what occurs when you have a closed interval. So as long as your function is continuous, which we're going to basically just be dealing with continuous functions on a closed interval, meaning we have endpoints, you're going to be guaranteed a global max and a global minimum. When the interval is open, for instance, if my function is defined from negative infinity to infinity, right? Meaning I would have like arrows here. Remember, our textbook currently doesn't put arrows on our graphs. So when there is no endpoint, like in this case over here, we assume that there are arrows there just to remind ourselves. And so this function, since it continuously goes up continuously forever to positive infinity, y equals positive infinity, or it approaches to positive infinity, this one has no global maximum, all right? It has no global maximum because the function continues to go up. However, it does have a local maximum, which is here at this point here, because this point has a y value that's larger than all of the y values that are of the points that are near it. It does, however, have a global and local minimum. This is not guaranteed, but at this critical point, I have a local minimum, and at this critical point, I have a local minimum. And since this is the lowest point on our graph, the point with the smallest y value, then this is also a global minimum. And so what we're going to want to do is we want to be able to find all of our global max and minimum points in addition to the local ones, right? And so when our interval is closed, we're going to search through our list of critical points and our endpoints. The one with the y value that's the largest is our global max. The one with the y value that's smallest is the global minimum. When we have a closed interval, we only have our critical points where we'll have a max or a min. And so we're going to search through our list of our critical points and find the one that has the greatest and the least value, and that will give us our global max and minimums. And so before we get there, just to get used to this, we're going to graph a function with the following properties. It has a local and global maximum at x equals 3, a global minimum at x equals 10, and the domain is from 0 to 10. That means, notice this is a less than or equal to and a less than or equal to, so x is between 0 and 10, and we include those values. Well, I'm going to have a global max at 3, so at x equals 3, I'm going to have my maximum point. They don't tell me what point to choose. I'm just going to choose the 0.34. That's my global maximum. I have a global minimum at 10. That means at 10, I have my smallest point, my lowest point. My domain of my function is from 0 to 10. That means my function starts at x equals 0 and it continues till I get to x equals 10. And so as long as this is the highest point and that's the lowest point, any graph that I draw would be fine, right? And so I'm going to have a situation. All right, I'm going to draw that a little better. Oh, that's the endpoint. I was about to put an arrow, but there we go. So that's my point here. That's a graph that represents that situation. And we know that since this is a local and global maximum, then this part of our function had to be lower. So that's why I picked a point here at 0, -2. You could have your graph going through the origin and going up to there, having a horizontal tangent line and going down, or what have you. But as long as this is the highest point, this is the lowest point, and my domain is from 0 to 10, you have a graph that's representative. All right, and we want to draw a smooth curve. All right, it says in example 2, let f of x equals x cubed minus 3x squared minus 9x plus 15 for -5 less than or equal to x less than or equal to 4. What this part right here does is it's telling you that you have an endpoint, you have endpoints on your function when you graph it, right? The leftmost endpoint is going to occur at x equals -5, and the rightmost endpoint is going to occur at x equals 4. So it's telling me I have this function defined on a closed interval. What we're going to do first is we're going to find the critical points of this function, right? To find the critical points, we find our derivative. We set our derivative equal to 0, and we solve for x. Well, in order for me to solve for x, I can factor. And so what I want to do is I want to review how we factor a quadratic polynomial. Well, the first thing we can do is we can notice that we have a greatest common factor. And so when we have a greatest common factor, we can factor that out. And what goes in parentheses is what we get when we divide each of those terms by that factor. Now, this is a polynomial with 3 terms, quadratic polynomials. They get factored into 2 binomials, right? I'm going to put an x here and an x here because when we multiply these out, we're going to get an x squared, right? And I have to find 2 numbers that have a product or multiply to give me -3, but add up to -2. Multiply to give me -3, add up to -2, -3, and +1 work. All right, so this is my derivative function equal to 0. I want to solve for x. One of the things that I can do is because this is just a 3, I can divide both sides by 3. We can never divide by 0. And I'm going to get x minus 3 times x plus 1. For me to continue to solve, I set each of those equal to 0. And I'm going to get x equals 3 or x equals -1. So my critical points are 3 and -1. All right, those are my critical points. And then what we're going to do is we're going to identify basically the local and global maximum and minimum values of f on that interval. Well, when you have your critical points, now what I'm going to do is I'm going to draw me a number line, but I'm not going to put arrows here because my function is defined from -5 to 4. I know that -1 is over here and 3 is going to be close to 4. Now, what I'm going to do here is I'm going to pick values on this interval so I can determine which of these are local or global, local max or mins. And I'm going to use my calculator to help me do this. So let's pull up our calculator here this time. And I'm going to use my y equals feature. If you don't have a graphing calculator, then just plug it into your derivative, right? So this is my y prime line, for instance. This is f prime. And so I'm going to pick numbers on these intervals. I'll pick a number like -3. I'll pick a number like 0 for that interval, and I'll pick a number like 3.5. I'm going to plug it into my derivative function and see if I get a positive or negative value. Now, when you're using your calculator, you can go back to this point right here. As you guys seen in some of my previous videos, I would go to the factored form, which is this step right here, and I would plug it in. Now, I would go to this step before I divide both sides by 3. Now, it's not going to matter in this example because that's dividing by a positive 3. If I were dividing by a -3, it could change my results completely. And so what I would do is I would always go to the completely factored form and plug in these values into, for x, see if I get a positive or negative result when I do that multiplication, and then that's going to be the sign there. I'm going to use my calculator, however, to do this. So I'm going to go to y equals, and I'm going to plug in 3x squared minus 6x minus 9. I'm going to press enter. I'm going to go to my table. So I'm going to go second window. And what I'm going to do is I'm going to scroll down and I'm going to make sure that ask is highlighted. And I'm going to press enter. Then I'm going to go to second graph to get me to table. And I'm just going to clear all that. Well, I guess I can't clear that out. I'm going to plug in -3. -3, press enter. I get 36, which is positive. Okay. I'm going to plug in 0. I get -9, which is negative. And I'm going to plug in 3.5, press enter, and I get a positive. So this is going to be a positive, negative, and a positive. Let's go and write this on our screen. I already forgot. Positive, negative, positive. And so what this means is that my function, not my derivative, but my function would be increasing on this interval, decreasing on that interval, and increasing on that interval, which means at x equals -5, I'm actually going to move this down a little bit. I wrote a little too big. So this means that x equals -5, my function starts at -5 and goes up. So this is a local minimum. Since it goes from increasing to decreasing, we see that we have a high point. So this is going to be at x equals -1, a local max. At x equals 3, it goes from decreasing to increasing. So we're going to have a local minimum. And then we increase until we get to x equals 4. So that's going to be a local max. And so there we have that. We know where our local max and our local minimums are by looking at our first derivative test and that number line there. All right, and we use our calculator to help us do that. And so now what we're going to do is we got to determine if they're global maximum and minimums, right? We already got the local stuff up here, but let's find the global. The global information about your function is going to come into effect by looking at the y values at these local max and mins. For instance, in this graph here, for me to determine whether this is a global max, I need to know the y value of the regular function, not of the derivative. The sign of the derivative tells me whether I'm going to have a local max or min, but I go back to the original function to see which point has the highest y value, and that's going to be my global max, and which point has the smallest y value, that's going to be my global min. So for this global information, I'm going to go to the x values of my maximums here, right, where x equals -1 and x equals 4, and I'm going to evaluate them. Right, I'm going to plug them into my original function, which is this x cubed minus 3x squared minus 9x plus 15. For my global minimum, I'm going to go to each of my original functions, and I'm going to plug, well, my only original function, and I'm going to plug in my minimum where my local max and my local minimums occur. They occur at -5, and they occur at 3. So go to your original function. You can do that same thing that we did on the calculator from before. we can go to y equals, I'm not going to go through this whole process, but you go to y equals, you put your original function here, and you go to your table set, ensure the ask is already highlighted, and then go to second graph to get to your table, and you can enter those numbers. When you do that, you're going to see that f of -1 is 20, f of 4 is -5, f of -5 is -140, and f of 3 is -12. So the global maximum is the point -120. It occurs at x equals -1, right? So this at x equals -1, we have a global max, a local max, and our global max, because that's the highest value. And our smallest value is at x equals -5, which is at that endpoint. So not only is that a local minimum, it's also your global minimum. And that point there is -5, -140. All right. So this is the general process we go through to find your global max and minimums. Let's look at another example where we apply this to an application. And we'll look at a function that is not as easy to solve. All right, I'll work with. It says the quantity of a drug in the bloodstream T hours after a tablet is swallowed is given in milligrams by Q of T equals 20 times the quantity e to the -t minus e to the -2t. It says when is the maximum quantity of the drug in the bloodstream? And then part B, what is the maximum quantity, right? So basically, this is asking us to find the global, the input value, because it's asking for when, which is a time, and my function is a function of t, which is time. So it's asking us the input value or the location of the global max, all right? And then this is the output value. It says, what is the maximum quantity? Well, my quantity is the output. And so this is the output value of our global max. All right, so this is what we're asked. And I'll remove that calculator so you can actually see the whole problem and scroll a little down. Sorry about that. But there we go. And so if I want to find my global max, the first thing I'm going to have to do is I'm going to have to find my derivative. So I'm going to have to find q prime of t. I have 20 times a quantity, right? Well, that derivative is going to stay in there. What I'm going to do is I'm going to use my distributive property. I'm just going to distribute that 20 to each of those terms. So this equals 20 e to the -t minus 20 e to the -2t, right? So let's take the derivative of 20 e to the -t, right? This requires the chain rule because that's not just a t, that's a -t, right? So my 20 is a constant multiple. The derivative of the outside will be e to the whatever power you have, but you have to multiply that by the derivative of your inside, which is -1. So that derivative of this first term is 20 e to the -t times -1. For our second term, that's 20 multiplied by that. The derivative of our outside, that's another chain rule because that's a -2t. That'll be e to the -2t. And on the inside is -2t, which is linear. The derivative of that is the slope, which is -2. So my derivative function is -20 e to the -t plus, because I do that, -20 times -2, which is a +40 e to the -2t. If I want to find my global maximum, I got to find my local maximums, right? So I set my derivative equal to 0 so I can find my critical points. This is where this gets difficult, all right? What we're going to have to do is we're going to have to factor, all right? Now, this is a 20 and that's a 40. So I'm going to factor out a 20. When the first term of what I'm factoring out is negative, I'm going to factor out a negative with it. Now, both of these terms have an e to the -t, right? This is e to the -t. This is e to the -2t. Now, let's think about this. This e to the -2t here. You can think of this as e to the -t squared, right? Or e to the -t times e to the -t, right? When you square something, you multiply it by itself. Either way, you can add these together, you're going to get a -2t, or you multiply those exponents, you're going to get e to the -2t, right? So this is actually e to the -t. This e to the -2t here is e to the -t multiplied by itself, right? So I can factor one of those out because both terms have it. And in this first term, since I factored out this entire expression, there's a 1 left. I factored out a negative 20. So if I divide 40 by negative 20, I'm going to get a negative 2. And I factored out one of these e to the negative t's. That's gone. And so I'm left with just one other. So if you remember your rules of exponents, you will be able to factor this. You just got to remember your rules of exponents. I'm going to slide this to the right. All right. So there we go. We have a product of two things and they equal 0. And so what we do, we set them both equal to 0. I have a negative 20 e to the negative t equal to 0, or 1 minus 2 e to the negative t equals 0. Now we have to remember how we solve exponential equations, which we did way back at the beginning of the semester. We isolate the exponential expression. That means we divide both sides by negative 20. Then we take the natural log of both sides. When you do that, you get negative t equals, well, the natural log of 0 is actually undefined. So this equation right here does not have a solution. Its solution set is the empty set. So this equation here does not have a solution. Let's solve this equation. Let's subtract 1 from both sides, divide both sides by a negative 2. And when we do that, let's get some more space here. We can take the natural log of both sides. The natural log and e cancel. That would be negative t equals the natural log of 1/2, which means if we divide both sides by a negative 1 or multiply both sides by negative 1, we get t equals a negative natural log of 1/2, which is approximately 0.6931. So our only critical point is 0.6931. We want to make sure that that is a max. So what I'm going to do is I'm going to do a Q prime line, right? And I'm going to put 0.6931 on that line. Now, I really want to put negative natural log of 1/2 on there. I know some of you are not comfortable, but it's approximately equal to that, right? Now, we want to find a global max, right? We need to know if we have open intervals or open endpoints, an open interval or a closed interval. This interval is actually half closed because since t is hours and hours is a time, our smallest value of t is 0, right? So this is an endpoint and my function can continue forever until infinity, technically, because time can continuously go on. And so my number line starts at 0. I put my critical point, negative natural log of 1/2 in there, and I'll extend that way. I want to pick a number between 0 and 0.6931, plug it into my derivative function. You can go here and plug it in, or you can go here and plug it in. Either way, you're going to need to use your calculator, right? And then I'm going to pick a number on this interval here. I'm going to go to my calculator and plug in my derivative function so that we can see what happens. All right, I'm going to plug it into, so I'm going to clear this out. I didn't mean to do that. I'm going to plug in the first one, negative 20 second e to the negative t. Well, our calculator is in x and y, so that would be e to the negative x. Then plus 40 e raised to the negative 2x. Now, if your calculator doesn't put your exponents in your exponents, make sure that you put that negative 2x in parentheses, because if you don't, then you're going to get it incorrect. I'm going to press enter, and I'm going to go to, I already got my table set, but just to make sure, second window, make sure that ask is highlighted, and it is. So I'm going to go second table. I'm going to pick a number between 0 and 0.6931, which is like 0.5. So let's put 0.5 in there. Press enter. I got a positive, and I'm going to pick a number bigger than 0.6931, a number like 1, and I got a negative, right? So I got positive, negative. Which meant that my function would be increasing and then decreasing, which makes x equals 0 a local minimum, and x equals negative natural log of 1/2 a local max. Now, if I only have a local minimum and a local max, which means my function is going to decrease on forever and ever, not only is this a local max, but it's also a global max because my function is basically going to do this. And it does that at the point, approximately 0.6931. So that's also a global max, which is what we're trying to find. And so it says, when is the maximum quantity of drug in the bloodstream? We can say approximately 0.6931 hours after the tablet is swallowed. All right, and that is the answer to number one. Part A. To part B, we have to find the output value of the global max, and that basically means what is the actual maximum quantity that goes back to the original function. We go back to the original function and we plug in the input value that we just found, right? So we need to find F, and I'm going to do negative natural log of 1/2 because that's the exact value. You can put this approximate 0.6931 value in there. I'm going to put the exact value in there. And what you're going to see is when you do that, you're going to get 5. And since that is a quantity and Q is measured in milligrams, your answer will be milligrams. And so this concludes that video. See you during the next one.